Hello and welcome to the second tutorial on my OCRAS chemistry series. Today we're talking about atomic masses, the mole, empirical formula, lots and lots of good stuff. But it's nice to do it all in one tutorial because all these things are interconnected. But if you ever want a separate tutorial, then just message me and request for one. First off, we're going to start with atomic masses, and they are the proportionality, actually, how much of one particular isotope is in two different isotopes. So, since they've given us the percentage composition of each of these two isotopes of bromine, we'll use the percentage and times it by their molecular mass. I worked out the molecular mass by looking at these names. The names just mean, oh, I'm bromine and I've got 79 molecular mass, I'm bromine and I've got 81 molecular mass. So combining the two sums, we will get 79.94, which is roughly the most common isotope of bromine, with a molecular mass of 79.9 to one decimal place. So we'll put 79.94. These four definitions read roughly the same, so I'll just go through them all and highlight the important differences between each definition. The relative isotopic mass is the mass of an atom of an isotope compared with 1/12 of the mass of an atom of carbon-12. Relative atomic mass is the weighted mean mass of an atom of an element when compared with 1/12 of the mass of an atom of carbon-12. Relative molecular mass is the mass of a molecule when compared to 1/12 of the mass of an atom of carbon-12. And relative formula mass is the weighted mean mass of a formula unit compared with 1/12 of the mass of an atom of carbon-12. So, be a good idea probably to write these on flashcards or get a textbook and cover it over your hand and just keep reciting these until you know like the back of your hand, because they're very, very useful definitions to remember. Right, moving on to part 2 now, we have the mole. This is the proportionality between mass and molecular mass. So the formula you need to remember is moles equals mass over mR, short for molecular mass. Now, if we take a gander at this example, antimony is found naturally in a number of minerals, including stibnite. Stibnite typically contains 5% of that. Antimony can be obtained by reducing that with scrap iron. So this and iron, reduce it to antimony and iron sulfide. So part 1, how many moles of that are in 500 kilograms of a typical sample of stibnite containing 5% by mass? This is the clue that you need to use the masses given to you in the question. So molar mass of this and relative atomic mass of antimony is 122. So starting it off, we times 25 by 1000, we get 25,000 grams of Sb 2s3. So 25,000 over 340 equals 73.53 moles. It's best to keep it to two decimal places, but always leave your calculator answer to the full calculator display. So if we look at our calculator, if you can see that I have my full calculator display there, and in the exam it's probably best to keep this in memory just in case you are asked to use your answer. But when rounding off, always round off to 2 decimal places, unless they tell you in the question. Some questions want you to use 3 significant figures. I've even seen questions asking for 4, but that's very, very rare. So part 2 is to calculate the mass of antimony that can be obtained by processing 500 kilograms of stibnite. So if you know the MR of antimony is 122 grams per mole, you know that the moles times the molar mass can equal the mass, because if you rearrange the formulae to make mass equals, it will always be moles times MR. So that equals 8970.66, but since they want it in kilograms, you just divide this figure by 1000, giving you about 8.97 kilograms. So that's a fairly standard exam question, but if you ever want any more examples, just look. There are quite a few examples in the textbook. You're looking for unit 1.1.3 to 1.7 for moles and empirical formulae. Or you can always hang around and wait until I upload a past paper question video on moles. So we're looking for definitions now. Mole is the amount of any substance containing as many particles as there are carbon atoms in exactly 12 grams of the carbon-12 isotope. Molar mass is the mass per mole of a substance. The units of molar mass are grams per mole. I put it to the -1 because it's the same as saying this. Per means divide in maths. Moving on to part 3 now, we're going to use moles in order to find out the ratios between compounds, but that is what empirical formula is. Now we're going to look at our percentages and take our percentages to be 100 grams. So if we put 55.5 over the mass of mercury and 44.5 over the mass of bromine, we should get our 2 ratios. So doing that, we get 0.276 moles and 0.556 moles. So now we divide by the smallest mole, as it were. So we have 2.77 moles over 0.277, which is 1. So we have 1 Hg molecule, well, atom. We have 0.5569 over 0.0277. I mean 2, not 0.02. So dividing that by that, we get about 2 see what I mean by they are whole number ratios? So for this particular compound, it would have an empirical formula of HgBr2. It's best to lay it out like I did, only a little bit neater. Always state your full number ratios, and then write your guess at the molecule afterwards, and then write your full empirical formula with proper periodic table symbols and clearly spaced out, just in case you get it wrong. Now, the next example I would like you to have a try at, and we'll see how you get on after this pause. Okay, hopefully you tried that example, and now I'll go through it. So 72 grams over 24.3 for magnesium. If you didn't know that, you can consult your periodic table. You can always consult your periodic table. And nitrogen is 14. Don't forget, you can, with empirical formula, you take the grams to be the percentages, as both of them always total up to be out of 100 unless the examiners do a silly typo. So once you work out those two values, don't forget to round it up to the nearest whole number now. So this particular one will be 3 and this one will be exactly 2. So you have Mg2 and N2 as your formula. Notice that I'm writing subscripts. You don't have 2 moles of each atom. You have simply 2 atoms of each per molecule. Okay, moving on to moles in gases and solutions. There are a few more formulae that you have to remember for moles, and it's number of moles in a solution. So number of moles equals the concentration times the volume all over 1000, because this is the amount in 1,000. This is for any solution, but this is to represent in centimeters cubed only, as 1,000 centimeters cubed is identical to 1 decimeter cubed, deci being the prefix for 1,000. But if you have your solutions in decimeters, you're going to want to just do concentration times volume, and I'll just put in dm cubed. So for gases, now you use the same units, decimeters and centimeters cubed. So you put number of moles, apologies for my rubbish writing. You put volume in dm cubed all over 24, and if you're working in centimeters cubed, then you just put the volume in centimeters cubed all over 24,000, as there are 24,000 centimeters cubed in 1 decimeter. So let's have a tackle at this particular question. This question looks at the reaction of sodium with water and oxygen. A chemist reacted 0.5 moles of sodium with water to form 50 centimeters cubed of aqueous sodium hydroxide. 2 sodiums and 2 moles of water make 2 moles of sodium hydroxide and 1 mole of hydrogen gas. What mass of Na was reacted? Now, if you would like to have a go at this question, please pause the video and have a go. Okay, so the actual mathematical manipulation you need to do is for the mass of sodium, you use 0.05 moles times the molecular mass of sodium, which is 23, to equal 1.15 grams. This is for part 1. So really it's just a simple rearrangement of moles times mR to equal mass. To calculate the volume of hydrogen gas in decimeters cubed, so you use your decimeters cubed formulae, you first look at your chemical equation and you tell yourself, how many moles of sodium do I need in order to make 1 mole of hydrogen gas? So the ratios are 2 to 1, so you have to divide your moles of sodium first to equal 0.025 naught. Let's make that a bit tidier. So knowing you have 0.025 moles, you times that by 24 decimeters cubed in every 1 mole of gas to get 0.600 decimeters cubed of hydrogen. If you want to know where the number 24 comes from, 1 mole of gas is identical to 24 decimeters cubed. This is assuming that it's at room temperature or at 25 centigrade C and 1 atmosphere pressure. But we'll come back to standard conditions, which is what this hoopla is about later as we tackle organic chemistry. So the volume for this particular one is 0.6 decimeters cubed. Calculate the concentration in moles decimeters cubed of sodium hydroxide that was formed. So your concentration would be the moles of sodium, no dividing this time, as you can see the molar ratios of sodium and sodium hydroxide are exactly the same, so you just times 0.5 by 20 to make exactly 1 mole concentration. So the important definitions you need to remember are: molar volume is the volume per mole of a gas. The units of molar volume are decimeters cubed per mole. Concentration is the amount of solute in mole dissolved per decimeter cubed, or 1,000 centimeters cubed of the solution. So hopefully what you've been taking away from this is how to calculate atomic masses. You times the percentage by the molecular mass to get your averages. So just add the two quantities together and you will get roughly the value it is on the periodic table. Some questions do throw a curveball in. If you do this exact calculation and read the questions really very carefully, you would usually pick yourself up a couple of 2 or 3 marks. You should have also learned that moles are not that bad, and how to manipulate them. The 3 equations to learn are moles equals mass over mR, moles in a solution equals concentration times volume all over 1,000, or if you prefer it in symbols, I'll put moles equals C times V all over 1,000. The final one you need to remember is moles in a gas, so it will be moles equals the volume all over 24, only if it is in decimeters cubed, but if it is in centimeters cubed you put it over 24,000. If it's in centimeters, put it in over 24,000. And the definition you should take away from this is the mole. Get your tongue around this one. The amount of any substance containing as many particles as there are carbon atoms in exactly 12 grams of the carbon-12 isotope. You can tell I practiced this one this morning. Molar mass is the mass per mole of a substance. The units of molar mass are grams per mole, or G per mole. I mentioned this earlier. G over mole is the same thing as that up there. It's just mathematicians like to put to the -1 because we want to save paper. And should have learnt empirical formula, which is the simplest whole number ratio of atoms in each element present in the compound. Don't forget to look up at the periodic table for the molecular masses and treat each of the percentages as if they were grams. So 55.5 over the mass of mercury, so 200.6, and so on and so forth. And for multi-stage calculations like this, don't forget to use your arsenal of the 3 different formulas that I mentioned earlier, and these definitions are very key for this part as well. Stick around on my channel, please subscribe, as I have past paper questions videos coming up very soon. Hopefully this will be useful in your revision, but well, I'm sure that will be very useful in your revision, because past paper questions are the only way to tackle moles, really. From experience, I've just practice